welcome you all in this NPTEL online certification course on mechatronics. Today we are going to discuss some basic concepts about the semiconductor electronics, because the various mechatronics component, especially the controllers, they are composed of so many semiconductor electronics, that is transistor, ICs, and so many things are there. Okay. So, emphasis of my today's lecture is to go through some basics of semiconductor electronics, so that when we come across these mechatronic devices or mechatronics components, we are able to correlate the things. So, as I said, one need to understand the physical characteristic of semiconductor which are used in an electronic circuit. We will see the physics of semiconductor and learn how electronics component are designed using different type of semiconductor materials. We will also learn the circuit schematic symbol for different semiconductor diode and transistor that are used in the circuit design. So, first of all, let us begin with the concept of energy bands in conductor, insulator and semiconductors. Okay. So, we can see that in any material essentially there are three bands. One is the conduction band, and then we have the valence band, and these two bands are separated by the forbidden band. Okay. And it is the conduction band which is responsible for the conduction of the current basically. Okay. And here if we are talking about say metals, in metals there are very large number of weakly bound electrons in the conduction band. Okay. And when a voltage is applied to metals, these weakly bound electrons migrate freely and they produce the current. Okay. So, we can understand the difference between conductor, insulator and semiconductor with the help of these two bands, that is the conduction and valence band, and the segregation between these two bands. So, let us look at here some of the figures. Say for conductor, we can see that we have a valence band and we have a conduction band. In the conduction band we have a we have electrons, there are much number of electrons are there, and the segregation between the conduction band and the valence band, that is the energy gap which we call at the forbidden gap, forbidden energy gap, this one forbidden band rather. Okay. This is very small or insignificant. Okay. So, this is there. If we talk about insulator, then we can see that in insulator there are very few electrons in the conduction band. Okay. There are few almost there are no electrons in conduction band rather in insulator, and there are few electrons in the valence band, and there is a very large energy gap between the conduction and valence band. That is, if an electron has to move from valence band to conduction band, very large amount of voltage is required and okay, to do so. Alright. So, that is there is a very large energy gap. So, there are materials which are in between the conductor and insulator, and that is what we call it as the semiconductor materials. Okay. Now, in case of semiconductor materials, the energy gap, the small energy gap, there is a small energy gap between the conduction and the valence band, and this figure illustrate you when a voltage is applied. So, these electrons basically they move through the positive side of the voltage supply, and they move in this direction. Okay. And so, our conventional current direction is the opposite of that of the electron motion direction, and we see the current being moving in this direction. Okay. So, as I was telling you about semiconductor basically. So, these are actually the class of elements in group 4 of the period table, which have properties between conductor and insulator. Okay. And as I said, these since their properties is between conductor and insulator, they are called semiconductors. So, ideally you can identify them with a very small energy gap. Okay. So, what happens if we look at the elements in group 4 of the periodic table, say we have silicon and germanium, okay, and the properties of pure semiconductor crystal can be significantly changed by inserting small quantities of elements from either the higher group or say group 5 or the lower group say group 3 of the periodic table into the crystal lattice of the semiconductor, and this process is what we call it as the doping, and these elements are called basically the dopants. So, as I was telling you, the silicon has got 4 valence electrons. Okay. So, if arsenic or phosphorus of say group 5 is added into the crystal lattice, then what happens, one of the 5 valence electron, we know 8 electrons are required for to get it what we call it as saturated, okay, to fine. So, after 8 electron, if silicon has got the 4 valence electrons. So, if we are adding arsenic or phosphorus which has 5 electrons. So, totally we will be having 9 electrons. Okay. So, the 8 electrons will be making it ideal basically. Okay. So, the one additional electron which will be there, that will be the free electron. Okay. And that remains freer to move around, and the dopant is called what we know as the donor. And since here electrons we have one extra electrons or one free electron rather, the resulting semiconductor is called a N type silicon, okay, due to the availability of the electron in the crystal lattice as a charge carrier. Now, if the silicon is doped with boron or gallium, say from the group 3, okay, then holes form due to the missing electrons in the lattice, where acceptor dopants atoms have replaced the silicon atom. Now, this is because the dopant atom only has got the 3 valence electrons. So, basically what you will be having is that you will be having say here 1, 2, 3, 4, say 5, 6, 7, 8. So, you have the total 7 electrons and there is a hole. Okay. So, there is a hole which is being created if I am putting an element that is element that is either boron or gallium, okay, from group 3 with the silicon. Okay. Now, this hole can jump from atom to atom and this produce a positive current, and this type of semiconductor is called a p type semiconductor. So, let us look at the p-n junction characteristic. P-n junction means that what we are doing essentially is that a p type semiconductor and a n type semiconductor we are putting it together. So, we have the p type semiconductor, we have the n type semiconductor. In n type semiconductor we have the electrons, the free electrons which are readily available to move, whereas in p type semiconductor we have the holes which are readily available to move. Okay. So, if there is no field applied across the two terminal of say this p-n junction, okay, then what happens that some of the electron jump from n side to the p side, as you can see here. Similarly, some of the holes jump from p side to n side, as you can see over here. Okay. And there is an internal contact potential which is around 0.6 to 0.7 volt that is formed. Okay. Now, what happens if I apply a voltage across the two terminal of this p-n junction. Okay. So, suppose I apply a voltage here across the p-n junction, so that my positive side of the source or anode is connected to the p type here, p type material, and similarly cathode is connected to the n side here. Then what happens basically, this negative side will be in contact with the n side here. So, these charges will be repelled. Similarly, the holes, the positive side being contact with the holes over here, there will be motion of the holes in this direction or the motion of the electrons in the opposite direction, and we will be having a flow of electrons, or what we can say is that the flow of current. Okay. So, here we can see that a negative that is electron is moving to this side. Okay. So, again here a hole will be created. So, this hole space will be again taken by an electron from here and so on. Okay. So, our effectively our electron will be flowing in this direction. Okay. And of course, your current direction will be the opposite one. So, this case where we can see that there is flow of current across this p-n junction is what we call it as the forward biased. Okay. And similarly, if we apply now the voltage across these two terminals in a opposite way, that is the positive side is connected to the n type of material and negative side connected to the p type of material, then what happens, because these charge will be attracted towards the anode, okay, the region, the depletion region here, okay, will be increasing, further prohibiting any motion of the electrons across the junction. Okay. And this is what is called as the reverse bias. So, in forward bias, as the applied voltage approaches the value of the contact potential, say 0.6 to 0.7 volt for silicon, the current increases exponentially. Okay. And this current is given by I0 exponential q Vd by kT minus 1, where Id is the current through the junction I0 is the reverse saturation current, Q is the charge of one electron, that is 1.6 into 10 power minus 19 coulomb, and K is the Boltzmann constant, that is 1.381 into 10 power minus 23 joule per Kelvin. Okay. And Vd here is the forward bias voltage across the junction, and T is the absolute temperature of the junction in Kelvin. Now, in case of the reverse bias, the reverse saturation current I0 does flow, but this current is very small, of the order of 10 to the power minus 19 to 10 to the power minus 15. So, that is why we consider, we assume that the current flow from the across the junction in case of reverse bias is almost 0. Now, here, so what we have seen that when the p-n junction is forward bias, okay, we get the current through it, and when it is reverse bias, there is no current. So, basically it acts, it passes current in only one direction, that is the case when it is forward bias. Okay. Silicon diode is that is why sometimes also referred to as rectifier, because it passes current from only one direction. Okay. So, this is how we represent it, that is you have a p junction, p-n junction over here, and there is a symbolic representation for it. Here the piece in the n side there is a vertical line, and there is a triangle over here, okay, and this positive and negative is shown, and this is the example device, say IN314 is a diode, and this is the direction of the current or forward bias current flow direction, that is the opposite to the direction of motion of the electron, which we consider, because we have seen that we assume that the electrons flow in this direction. This figure shows basically some of the commercially available common diodes. So, you can see a small signal diode, power diodes are there, then LEDs or light emitting diodes are there, and 2 digit or 7 segment LED displays are there. So, you can see that there are 7 segments here, 1, 2, 3, 4, 5, 6 and 7. So, these are what we call 2 digit 7 segment display, because we can display the 2 digits with the help of 7 segment. Again this figure shows you some of the commercially available diodes. Now, I just in the previous slide discussed that there is a current flow if it is forward bias, and there is no current flow if it is reverse bias. Okay. So, if we plot the voltage and current characteristic curve for the diode, then you can see that this is how it looks like. So, ideally what happens that with a small voltage in the forward bias, you are going to get a very large current, as you can see here. Okay. Whereas in the reverse bias, as you keep on increasing the voltage, but your current is not going to change. Okay. So, this is what is there. Now, the real diode curve is something like this, that there is a exponential growth, basically exponential growth in the current value in the forward bias region. Okay. And that gets a peak basically for a silicon diode around 0.7 volt. Okay. And approximation of the real diode can be done with the help of dashed line, as it is shown here. So, this is the behavior in the forward bias region. Now, in reverse bias region what happens, as I was telling you, in case of real diode what happens, if you keep on increasing the voltage, initially there will not be a current, but in the breakdown region you are going to have at a high voltage you are going to have the increase in the current value, okay, and ultimately it leads to the failure over here, okay. And this steep increase is basically increase in current as almost constant voltage is helpful in designing the voltage regulator, what we call it as the Zener diode, which I will be discussing in the coming slides. Okay. So, we have the forward bias region, this is the behavior, and this is the reverse bias region, and this what we call it as the breakdown region, because here the failure takes place. And you can see that here the current magnitude is in the micro range basically, okay, microampere, whereas when it is forward bias we have it is in the milliampere range. Now, this characteristic of the diode, that it allows current only in one direction, can be used for the rectification purpose. Okay. So, here suppose I have got a voltage source, okay, VI, and this voltage is varying say, okay, and let there is a circuit where we have a resistor, and I am putting diode over here, and from this diode I am typing the output voltage. Okay. So, here there is a sinusoidal input over here. So, you can see that sinusoidal input, that is the voltage goes, input voltage is both in the positive side as well as in the negative side, and we want to rectify it. So, that is we want it only in the positive side. So, here what happens, you can see that when Vi is positive, okay, when Vi is positive and this is the negative side of the diode, okay. So, this positive and this is negative. So, what happens, this becomes the reverse bias, okay. This diode gets reverse bias. Now, in reverse bias there is no current flow. So, when there is no current flow from the diode, then what happens, whatever Vi is there, the same Vo is available across the terminal. So, this input, okay, is whatever is there, we have the output over here, okay. And in next half of the cycle, this becomes negative, and this of course is negative. So, this diode becomes the reverse bias, and in reverse bias this diode becomes the forward bias, and in case of forward bias there is flow of current. So, there is no voltage drop across this one. So, we have the voltage 0 here across the terminal. Okay. So, this is how we get the voltage rectified. Okay. So, I will repeat again, when Vi is negative, diode is forward bias, and we have a its equivalent to a short circuit, thus no voltage drop across diode. So, we get the 0 voltage, and this cycle repeated. Now, we can use the same diode circuit, okay, in a say bridge fashion, okay, to rectify it, okay, or what we call it rather a full bridge rectifier. So, I have a AC line input, say VAC is there, this is the nature of the input supply. I have a transformer which say step down transformer here, okay. So, the voltage is reduced with the help of transformer. Now, this secondary winding of the transformer is connected through diode, okay, and this diode rectifies it, okay, and then there are filters and regulators, and this filter and regulator gives us the constant voltage, okay. That is the constant voltage which can be obtained across the DC load. Now, how does this work basically? It is simple. So, if there is a positive input basically, so this is positive side, okay. This is positive side. So, what happens, your this is positive side. So, positive side being connected to the positive side. So, this is being forward bias, okay. So, your current will be passing from here, okay, and similarly this is positive side connected to the positive side, so forward bias. So, this these two electrons basically work in the forward bias, whereas you can see that this positive side being connected to the negative side, this makes this and this diode in the reverse bias, okay. So, this way are the two these two diodes are in the forward bias mode. Similarly, so current flows and we can get the voltage across the here load here. Similarly, if it is negative, voltage here is negative, then these two diodes are in the forward bias, okay. So, current flows through them and then we get the output voltage here. So, here are the diode bridges which are commercially available in the market. The cylindrical device on the right in the photograph has a current limit of 1 ampere, physically it is 7 millimeter high and 10 millimeter in diameter. The flat device on the left has a current limit of 4 ampere, it has a thickness of 6 millimeter and 16 millimeter height and 19 mm width, and photograph on the right shows a large high power diode bridge. It has current capacity of 15 ampere and peak reverse bias voltage of 400 volts. So, these are the commercially available. Now, let us discuss or let us exploit the characteristic of the diode in the reverse bias, where what I said that in case of reverse bias, if we keep on increasing the voltage. So, when the voltage is very high, there is some current which we are getting, okay, and this characteristic is used as the voltage regulator. So, most diode breakdown voltage is around 15 volt, and these have steep breakdown curve, as I said, with well defined breakdown voltage, and thus they maintain nearly constant voltage over a wide range of current. Thus, they are good voltage regulator, and this property to properly use the Zener diode in a circuit, the Zener should be reverse bias with a value kept in excess of its breakdown or Zener voltage. Okay. So, here we can see the schematic symbol of the Zener diode. Here you can see the difference, whereas for the normal diode the symbol is this one, okay. But in case of Zener one we have a different symbol, and this is the VI characteristic of it, and here we are interested the Zener being reverse bias. So, here you can see that the voltage where we get current, okay, which is called a Zener voltage, and this is the operating point around which we want this to operate. Here dashed line shows ideal Zener diode characteristic in the forward and reverse bias. Okay. So, if we see Zener as a voltage regulator, then say I have got say a circuit with a voltage Vi, there is a resistor R and here is a Zener diode, and I am interested in using this Zener diode as a voltage regulator basically, that is the one which gives me a constant voltage. Okay. So, if I analyze this circuit, say if I apply the Kirchhoff voltage law, then you can see here my minus Vi plus IZRR is here, and then plus what your Vz, this is equal to 0. Okay. So, what I get is basically Iz is V I minus V Z by R. So, I get this relationship. So, change in the this Zener current basically will be delta V I minus delta V Z divided by R. So, here we can see that it is a non-linear relationship basically. Okay. To take care of that, what we do is that we define what do you say is that dynamic resistance R d, and say this I z is will be then delta V z by R d. So, we define this dynamic resistance like this, and if I substitute back this equation in the previous one, this is what I get as the output. So, my delta V o is delta V z, and this is delta V I times R d by R d plus R. So, this factor basically gets multiplied to your input voltage, and whatever is there you get that as the constant voltage source. Then there are light emitting diodes basically. These are the diode that emit photons when forward bias. Okay. So, this is the schematic representation for this, and this is a schematic symbol. Okay. So, photons being emitted when this is forward bias. Okay. And similarly, there are photodiodes which works in a reverse way basically, that is if light falls on them a current is produced. So, these are designed to detect the photons and can be used in a circuit to sense the light. So, photodiodes can basically work as a light sensor. Okay. So, there next coming next few minutes I will spend in discussing about a very important component semiconductor device called transistor, which has revolutionized the electronic industry basically. Okay. So, there are two types of transistor, that is the bipolar junction transistor and field effect transistors. So, in short they are called BJTs and FETs. Okay. So, the bipolar junction transistor basically consists of three adjacent diode. We had the two adjacent region, one was p type material, another was n type material. Okay. Here we have the three adjacent regions of doped silicon, each of which is connected to an external load. Okay. There are two types of BJTs, that is either NPN or PNPs. Okay. It consists of how we are bridging basically these three regions basically. Okay. So, it consists of a thin region or layer of p type silicon sandwiched between the two layer of n type silicon. Okay. And three leads are connected to the three regions, and they are called collector, base and emitter. So, this figure you can see that this is a NPN transistor basically. So, this is the p type silicon, we have n type silicon here. So, the one n terminal is connected here, which is called collector, one central one is called base, and here this is called emitter. Okay. So, the n type silicon is the n type silicon in the emitter is more heavily doped than the collector here, as you can see in this figure. So, basically we cannot interchange that, we cannot make emitter as the collector and the collector as the emitter. Okay, because their doping is different. So, these are not emitter and collector are not interchangeable. Okay. Here is the representation basically for this NPN transistor basically. So, we can see that the base voltage VB is shown here, emitter voltage is shown here, collector voltage is shown here. Okay. So, it is shown the direction of current of through the base, through collector, and through emitter is basically it is a summation of base and collector current is there, and we can see that the VCE is greater than 0 and VBE is greater than 0. So, VCE is basically voltage between the collector and emitter, and B is the voltage between the base and emitter. So, these are the basically how they are defined. VB is basically VB minus VE, VC is VC minus VE, and IE is IB plus IC. Normally, VC is greater than VB and greater than VE. So, we can see that BE junction is forward bias and BC junction is reverse bias. Okay. So, that is there, and IB controls, that is the base current controls the collector current, and it acts as a current amplifier. So, basically this amplification is say beta times the collector current is beta times that of the IB. Okay. So, the transistor connection, there are various types of connections, say common base, common emitter, and common collector connections are there. Okay. So, in my coming lectures we will be seeing how these transistors can be used for the different purpose. Okay. So, and most importantly is the transistor as a switch. Okay. So, that we will be seeing in our next lecture. Okay. So, these are the references. Most of the material for this lecture has been taken from very good book, Introduction to Mechatronics by Alcier Tor and Histand. So, if you are interested in further reading, please do refer it. Thank you.